The objective of this screencast is to show how to determine Laplace transforms of graphical functions. As you've seen here on the screen, we have a graph which increases from 0 to 20 linearly over 10 minutes and then stays at 20 for the rest of the time. Also provided is the definition of a Laplace transform, which is integral from 0 to infinity of the function multiplied by e to the negative st. So what we need to do here in order to find the Laplace transform is put the graph that we have on the left into functional form. It's a piecewise function where we'll have that f of t, which would be y in this case, would equal some linear function from 0 to 10. And then we have the fact that the function is equal to 20 for all times greater than or equal to 10. So in order to find what this linear function is, we need to find the slope m and the intercept b. Based on the diagram, it's quite straightforward to determine the fact that the y-intercept here is 0. And then for the slope, we'll have the change in y over the change in x, which is going to equal 20 minus 0 divided by 10 minus 0. So therefore, the slope here is 2. So we can restate our piecewise function as y, which is f of t, equals 2t from 0 to 10, and that y will equal 20 for all times greater than 10. Now that we have the piecewise function, we can now use the Laplace transform equation. So therefore, our Laplace of y is going to equal the integral of 0 to 10, the first part of our piecewise function, 2t e to the negative st dt, plus the integral from 10 to infinity of 20 e to the negative st dt. We will now integrate these two terms. We're going to start with the second term because it is simpler to integrate. So the second integral is going to be negative 20 over s multiplied by e to the negative st, evaluated from 10 to infinity. When we evaluate this from 10 to infinity, we end up with negative 20 over s multiplied by e to the negative s times infinity plus 20 over s e to the negative s times 10. Since s times infinity will cause an exponential raise to the negative infinity power, this term will go to 0. So that leaves us with the second term just being the 20 over s multiplied by e to the negative 10s. For our first integral, this is a classic integral which can be solved via parts. So here we'll define u as 2t, meaning the fact that du is 2. And then that means the fact that dv will be e to the negative st dt. And v will be the integral of that, which will be very similar to what we just did, which is negative 1 over s e to the negative st. So recall that from parts, when you do this integral, it ends up being uv minus the integral of v du. But remember the fact that since this is a definite integral, we have to evaluate uv from 0 to 10, and similarly, the integral will be from 0 to 10. And the last one we have here is coming from the third term. What you'll notice here is that the first term and the last term will cancel out, which means the fact that our final answer will just simply be the evaluation of the second term. When we evaluate the second term, we'll have negative 2 over s squared multiplied by evaluation of e to the negative st at t equals 10, so e to the negative s times 10, minus the evaluation of e to the negative st at t equals 0, so negative es times 0, and this value will just be 1. So that'll leave us with our function in the Laplace domain equals negative 2 over s squared multiplied by e to the negative 10s minus 1. where this can also be restated as positive 2 over s squared multiplied by 1 minus e to the negative 10s. So this shows how we can turn a graph, which can be represented often as the input forcing function, and how we can transfer that into the Laplace domain for appropriate analysis of solving the equation. Therefore, this screencast shows how to turn a graph in the t-domain into a function in the Laplace domain. Why this becomes important is the fact that oftentimes we analyze changes of outputs occurring due to a change in input. And oftentimes, although an input can be as simple as a step or a ramp function, sometimes it's a bit more complicated. And therefore, we need to be able to transfer that more difficult input forcing function and put it into the Laplace domain.